Greetings. So welcome to today's class. So if you recall, we were looking at Bode plots, and we were looking at Bode plots of each factor, right? That can be considered to be the building block of a transfer function. So we essentially were considering the second order factor of the form omega n squared divided by s squared plus 2 zeta omega n plus omega n squared. We calculated the corresponding sinusoidal transfer function, and we observed that like the low frequency asymptote when the frequency was much lower than the natural frequency was the 0 decibel line, and the high frequency asymptote when the natural frequency when the frequency is much higher than the natural frequency was minus 40 log omega by omega n. So consequently, the slope of the high frequency asymptote is minus of I'm sorry, it should be minus 40 decibels per decade. Okay, so please correct that. It's not 40; it's minus 40 decibels per decade. Okay. So we saw that, and as a result, the corner frequency, right? That is the frequency at which the low frequency asymptote and the high frequency asymptote intersect one another was the natural frequency omega n. Right? So these are the some basic facts, right, regarding this particular factor. Now we stop with the question as to when this magnitude, right, of this particular factor be a maximum. So let's continue from there. So if you recall, the magnitude of this factor d of j omega will be 1 divided by square root of 1 minus omega square by omega n square, the whole square, plus 2 zeta omega by omega n whole square. Okay, so this is what I'm sure all of us can recall as the magnitude of this particular factor. Okay, so now the question becomes when this becomes a maximum, right? So we can immediately observe that this is a function of omega, and as we know, if you want to maximize the function, you need to essentially take its derivative, equate it to 0, get the solution, and then take the second derivative and essentially go figure out whether the second derivative is negative, right, at that point. So an easier way to do this in this particular case is the following, right? So we can immediately observe that d of the magnitude of d of j omega would be maximum when let's say we call this a function as some f of omega. The function f of omega is 1 minus omega squared by omega n squared whole square plus 2 zeta omega by omega n whole square is minimum. Okay, so this is the crux. Okay, so what do we mean by this? That is, if we essentially have this function, right, which is appearing in the square root term of the numerator to be a minimum, the reciprocal of the square root is obviously going to be a maximum, right? So it's a very simple argument, right? I'm sure all of us can follow that, right? So consequently, we want to minimize f of the omega, so we just differentiate it with respect to omega. So I'm just going to take the first derivative of this f of omega with respect to omega. So what will we get? We get the first factor will be 2 times 1 minus by omega n squared, right? Then we need to take the derivative of 1 minus omega squared by omega n squared. That will be minus 2 omega by omega n squared, right? So that's what we get for the derivative of the first term, right? Then we have the derivative for the second term. We will have 2 times 2 zeta omega by omega n multiplied by, then we take the derivative with respect to omega of the factor within the square. So we'll get 2 zeta by omega. Okay, and this should be equal to 0, right? So that's what we will have. So if we essentially simplify these terms, of course we can cancel off some terms, right? So this 2 and 2 are common, right? And another factor of 2, right? This and this 2 and this 2 we can cancel out, right? Omega n squared and this omega n we can cancel off, right? And we can essentially have this, right? Okay. So this is what we have. So if we simplify and write down what we are left with, okay, let me write down what we have now. We have omega multiplying 2 zeta squared minus 1 plus omega square by omega n square. Okay, that should be equal to, all right. So if we have, let's say, this sort of structure, see if, for just to give an example, let's say if the product of 2 terms is equal to 0, if A times B is equal to 0, A can be 0, B can be 0, or both can be 0, right? All right. So in this particular case, this omega is multiplying the term within the square bracket and the product is 0. So omega can be 0 or the square, a term in the square bracket can be 0 or both can be 0. But however, omega cannot be 0, right? So it doesn't, we are not looking at a function becoming maximum at omega equal to 0, right? So that is not what we are searching for, right? So consequently, we have the term within the square root to be 0 as the solution of interest. So if we do this, we will get this to be equal to 0. And if we have, if we simplify this, we will essentially have this, right? Omega to be equal to omega n times square root of 1 minus 2 zeta. This frequency is what is called as resonance frequency. So I have included a subscript R to indicate that this frequency is the resonance frequency. Okay, so I hope it is clear what is meant by resonance frequency. So what is resonance frequency? Of course, we are going to get a condition on zeta as to when this frequency is meaningful and when we will get the maximum value and so on, right? As we go ahead. But however, we will essentially see that this is the frequency at which, the magnitude of the sinusoidal factor, right, is a maximum. That means that we provide a sinusoidal input of certain amplitude, and if the frequency of the sinusoidal signal happens to be this omega r, then this becomes the magnitude or the amplitude of the output, right, becomes the maximum, because the magnitude of the sinusoidal factor is the maximum at this particular frequency. All right, so that is resonance. Okay, and this is what is called as resonance frequency. Okay? So that's why resonance and resonance frequency are linked with this. That's how they are linked with frequency response. Yeah, I hope it's clear. All right. So now, if we look at this resonance frequency, when do you think it is meaningful to talk about resonance frequency? So we can immediately see that it is meaningful to talk about this resonance frequency only when 1 minus 2 zeta squared is greater than 0, right? Do you agree? Why? What happens if 1 minus 2 zeta squared is equal to 0 or less than 0?
Imaginary value.
So you see that if it's equal to 0, the resonance frequency is undefined, and if it is less than 0, it becomes an imaginary value, right? So we can have that, right? So by using physical motivation, we can immediately see that zeta has to be less than 1 by root. Okay, so for resonant frequency to be meaningful, the value of zeta should be between 0 and 1 by root. So the phenomenon of resonance itself, okay, happens only when the damping ratio it falls between 0 and 1 over square root of 2. All right. So that's something which is very, very important. I hope it is clear. All right. So in fact, one can, what to say, essentially show this by looking at the second derivative of this function. Okay. So if we take the second derivative of d squared f d omega square, okay. So what are we going to get if we have the second derivative to be evaluated? We will see that we will get 2 zeta squared minus 1 plus 3 omega squared by omega n. Sorry. All right. So then this is multiplied by 4 by omega. Okay. How did I get this? I got it from here. Okay. So instead of cancelling, if we look at this, we will see that this is nothing but, if we simplify this, this is going to be 2 zeta squared minus 1 times omega plus omega cubed by omega n square, multiply the whole thing multiplied by 4 by omega n square. So we are just differentiating it once again with respect to omega. So that's how we get. All right. So this we can immediately observe that this is going to be, if we substitute, right, omega to be omega r, which is omega n times square root of 1 minus 2 zeta square. If we make the substitution, because we are evaluating the second derivative, what do we get? We get, sorry, why is this happening? Okay, so we will get 1 minute, 2 times 2 zeta squared minus 1 plus 3 times 1 minus 2 zeta square, because we substitute for omega r, right? Here, right? Omega r squared will be omega n squared times 1 minus 2 zeta squared. So omega n squared and omega n squared will get cancelled off. And so then we will have 4 by omega n. Right? So then if we simplify this, this will become 2 times 1 minus 2 zeta squared times 4 by omega. Now this has to be greater than 0, right? For f of omega to be a minimum, right? So we are looking at f of omega to be a minimum. Then the question becomes, when will this be a positive number, right? So this will be positive only when this factor 1 minus 2 zeta squared is positive. Sorry. Okay, 1 minus 2 zeta squared should be greater than 0, because 2 is anyway positive, 4 by omega n squared is also positive, right? So even from this mathematical argument, we see that zeta should be less than 1 by root 2. Okay, so what this means is that the resonance frequency omega r is meaningful or exists, okay, by definition, only for underdamped second order system with zeta being greater than 0 but less than 1 by square root. All right. So that's what we have. Okay, as far as resonance. So I'm just going to recap 3 important frequencies. Okay. So and I want you to also like help me in recollecting the definition. Okay. So what is natural frequency to begin with? Omega n. What is the definition of natural frequency? So I told you that we will look at natural frequency, damped natural frequency, and resonance frequency later on, right? When we do frequency response. So here we are, right? So what was the definition of natural frequency? So you recall a second order system, right? Mass spring damper system. We perturbed it, and under what to say, that perturbation, what is the frequency at which the undamped, unforced system will oscillate, right? That is the natural frequency, and that is true for any degree of freedom system. So the natural frequency of the system is the frequency at which the undamped, unforced system will oscillate when perturbed, right, from its initial equilibrium state, right? So that is natural frequency. Point number 1. Damped natural frequency, if you recall, we encountered when we were calculating the step response, right, of underdamped second order system, and we defined the damped natural frequency as omega n times square root of 1 minus zeta square. Of course, this is meaningful only when zeta is between 0 and 1. So what is the definition of damped natural frequency? So as we discussed, it is meaningful only for underdamped second order system, right? So if you have an underdamped second order system, the damped natural frequency is the frequency at which the output of the system would oscillate, right? When provided an input, like a step input or an impulse input, right? Before it asymptotically settles down, right, to its final value. So that's why it's called damped natural frequency, and it makes sense only when zeta is between 0 and 1. Okay, please. So now resonance frequency is something else, right? So we can immediately see that resonance frequency is meaningful only for a subclass of underdamped second order system with damping ratio between 0 and 1 by root 2. And what is the physical meaning of resonance frequency? It is the frequency at which the magnitude of the sinusoidal transfer function is maximum. Okay. In other words, if we are giving sinusoidal signals, right, of the same amplitude or magnitude but of varying frequency, right, the resonance frequency is the frequency at which the output sinusoid will have the maximum amplitude. Okay, so that is the physical meaning of resonance frequency. All right. So I hope this point is clear. All right. Okay. So any questions on this? Okay. So now with this, let's plot the magnitude plot of the second order factor against the asymptote. Okay. So let me plot it very carefully. So this, we are plotting the magnitude of this. Okay, we are plotting as D, right? D of j omega decibels. This is omega, right? So let's, omega n is our corner frequency. Typically, we plot one decade above and below, right? The frequency range of interest. So we go from 0.1 omega n to 10 omega n. So let us say we start at 0, then we go to minus 20, then we go to minus 4. Okay. So let's plot the low frequency asymptote. The low frequency asymptote, as we know, is the 0 decibel line. It is this line. Okay, the high frequency asymptote meets the low frequency asymptote at the corner frequency, and it has a slope of minus 40 decibels per decade. So the high frequency asymptote can be drawn in this manner. Okay, so this has a slope of minus 40 decibels per decade. Okay, and what happens to the actual curve? So if we were to plot the actual curve of the second order factor, there'll be a series of curves. Okay, let me plot how they look. So they are going to have 0 as the low frequency asymptote, and then they will peak at omega r. Then it will go down, and then it will go along this high frequency. Right? I hope it's clear. Okay, so what? Sorry. Okay, so this is what. All right. So, but then this depends on the value of zeta, right? So this is omega r. So this is the peak. Okay, this corresponds to the peak, which is omega r, as we know, is defined as omega n times square root of 1 minus 2 zeta square. So immediately we can see that omega r is smaller than omega n. Point number 1, right? And as we what to say, increase the value of zeta, we can immediately observe that omega r is going to shift to the left, right, away from omega n, right, because the square root term keeps on, what to say, decreasing, right, with increasing zeta. So what will happen if I increase zeta? So this curve will essentially become something like this. Okay, the peaks will keep on shifting. Okay, to the left. Okay, so this is the peak. This is the peak, and so right. So consequently, as zeta increases, we can observe that the peak, okay, keeps shifting to the left. All right. So that's what happens. All right. So this is the what to say, corresponding magnitude plot, right? The asymptotic and the actual magnitude plot of this second order factor. All right. I hope that is clear. So any questions on how we got it? So now, what happens to the phase plot? So the phase plot is interesting. As we know, the phase, any questions on the magnitude plot? You know, like this is how the log magnitude plot or the magnitude plot of the second order factor will look like. Okay, so we are going to have a low frequency asymptote of 0 decibels, a high frequency asymptote having a slope of minus 40 decibels per decade, and we have the actual curve exhibiting a peak at the resonance frequency, and the resonance frequency keeps on shifting to the left, right, from omega n as we increase the value of zeta. Okay? So that's what happens. Okay, fine. Any questions? Okay. If not, we move to the phase curve. I'm just going to plot the phase curve. So what happens is the following. So as we know, the phase of the transfer function is this, right? The second order factor. It so happens that the phase will go from 0 to minus 180 degrees, with the phase being minus 90 degrees at the corner frequency. Okay, so that's what will happen as far as the phase diagram is concerned. So I'll just plot the phase diagram. So the phase plot will look something like this. So if you plot the phase diagram, so we are plotting the phase of this transfer function in degree. So once again, we go from omega n, 10 times omega n and 0.1 times omega n. So what will happen is the following. So let us say we go from This is 0. Let's say this is minus 90, this is minus 180. So what's going to happen is the following. The phase will be minus 90 at omega n, and what will happen is that the phase will go from 0 degrees to minus 180. Okay, but at omega equals omega n, the phase will be equal to minus 90. Okay, so if we plot the phase plot, what's going to happen is that like we are going to have so we'll have an inflection point here. Okay, and this will go down. Okay, and as zeta increases, we are going to get a family of curves which are going to look like this. Okay, so as zeta keeps on increasing, it gets sort of like more opened up. Okay, but it's going to vary between 0 and minus 180, but the pattern or the profile, right, of the curve, right, is going to change. Like this. Okay, so that's how it's going to look. All right, as zeta. So these are the what to say, the magnitude and the phase plot of this factor, right? Omega n squared divided by s squared plus 2 zeta omega n s plus omega n. All right. So I'm going to leave you with some exercises as far as this particular factor is concerned. So as an exercise, please find out what will be the magnitude of this d of j omega factor at omega equals omega r. Okay, that is problem 1. And what is the phase of this d of j omega at omega equals omega? So what you need to do is that in the expressions for the magnitude and phase, right, of this factor, you substitute omega equal to omega r, right, and then like we can evaluate the magnitude and phase. All right. So that I leave it as an exercise. As a third exercise, okay, construct the Bode plot of the reciprocal. So what is the reciprocal of this? It is s square plus 2 zeta omega n s plus omega s. All right, divided by. Okay, so this is the reciprocal factor, okay, as far as the Bode plot. Okay, so now this it completes the set of all factors, right? So if you look at all the factors that we considered in the very first class, right, as far as plotting the Bode plot was concerned, so if you recall, we had all these factors, right? So the constant 1 by s, yes, 1 by ts plus 1, ts plus 1, and the second order factors that we consider today, right? So put together all these factors, can be combined together to get the Bode plot of any given transfer function. Okay? So that is the idea. All right, and we make use of the fact that we are using log magnitudes and we are plotting frequency using the logarithm scale to our advantage. Okay, so we will do an example in the next session. Okay, wherein we will start from scratch and then plot the entire Bode diagram. But however, like I just want to give a generic concept about what we will observe in general, right? So suppose we have a plant transfer function, right, which is of the form n of s by d of s. So the numerator is of order m and the denominator is of order n. Okay, let us say this is a stable system. Okay, all poles and zeros lie in the LHD. Okay, so let's consider this. So one interesting result, okay, like which I'm just going to state, all right, which will also motivate us why we chose minus 90 degrees rather than 270 degrees and so on, right? So I think even that question was raised a couple of classes ago, right? And I told that I will answer it as we go along. So even if you recall, let me go up. If you recall, even for this factor 1 by s, right? I wrote the phase as minus 90 degrees, right, rather than plus 270 degrees, correct? So why? Let's learn some generic concept behind this. It can be shown, okay? I'm not showing this, okay? It can be shown that if you consider the P of j omega, okay, if you plot the magnitude of P of j omega as a Bode plot, as a magnitude plot, log magnitude plot, okay, it will have its slope of minus 20 times n minus m decibels per decade as omega tends to infinity. All right? Okay, so we are having a stable system because all poles are in the left of complex plane, and all zeros also are in the right left of complex plane, right? So if you recall, we have this to be the case. All right. Then it can be shown that not only for this, but for any generic transfer function, the magnitude plot will always have a slope of minus 20 times n minus 1 decibels per decade as omega tends to infinity. We can immediately, apply this and see, right? Because even if you look at the second order factor that we considered just now, right? So we can observe that the value of n was 2, right? Here, the value of n is 2, the value of m is 0, right? What was n minus m? It was 2. So minus 20 times 2 is minus 40, and that was the slope of the high frequency asymptote, right? So minus 40 decibels per decade was the slope of the high frequency asymptote in this particular example. Okay, so immediately we can observe it. Now, the phase of P of j omega tends to minus 90 degrees times n minus m as omega tends to infinity. So this, of course, holds true only for what is called as a minimum phase system. Okay, we will shortly recap what this is. So, of course, we are considering stable system. Okay, so if we have what is called as a minimum phase system, okay, so what is a minimum phase system? Minimum phase system, that is all zeros in LHD. Zeros, if they exist in the left of complex. Okay, so if you have a minimum phase system, then it can be shown that the phase of the sinusoidal transfer function as omega tends to infinity, okay, will be minus 90 degrees times n minus m. Okay, so that can be shown. All right. So this is a very important result. Okay, so because we can immediately observe that this is something which can be used to also experimentally figure out whether a system is a minimum phase by using experimental data, right? Because let's say you experimentally get the Bode plot, right? A system which you will be doing in one of the projects, right? By using the experimental data, we will reconstruct the Bode plot and then try to interpret the Planck transfer function, okay, experimentally. So by looking at the slope of the high frequency magnitude plot or the high frequency magnitude, we will be able to figure out n minus 1 because the slope of the high frequency asymptote is going to be minus 20 times n minus 1 decibels per decade, right? And if we are having the high frequency phase to be minus 90 degrees times n minus n, okay, then we know that the system that we are dealing with is a minimum phase system, right? So that is a very useful result, like which would be applicable or which would be beneficial as we go along. Okay, when we want to analyze experimental data and we want to figure out the transfer function. Okay, so now we see that that's why when we do this analysis, we take this phase to be minus 90 degrees rather than plus 270 degrees. Okay, so to essentially have this physical intuition, okay, to the entire process, right? So we look at the problem in this perspective, right? We will, as I mentioned, we will later do a project where you will be given the frequency response data of an actual system from experiment. You will construct the Bode plot from the frequency response data, and then we need to sort of like figure out what will be the transfer function. So that is the inverse problem, right? See, what we have done is that we have essentially what we have been learning is that like we have given a transfer function, okay? We are learning how to plot the Bode plot. See, that's why all this theory helps, right? Of course, as I mentioned, we can always use MATLAB and other tools to get the Bode plot very easily, right? So the command in MATLAB is Bode. But the reason why we are spending so many classes learning about the Bode plot and all these factors is because in real life, when we get experimental data, we need to interpret them, right? So that's where this theory would be useful. Okay, so please remember this theory. We will apply that, right? So in real life, we will have the Bode plot. The question then becomes, how do we interpret the transfer function? So to do that, we need to know how the Bode plot of the individual factors will look like, right? So is it not? Only we can go back and figure out the transfer function given the Bode plot. That's where we are heading. All right. We will essentially learn that technique, right, as we go along. So, but that we are going to use the what to say attributes of the Bode plot of the individual factors that we have learned till now. Fine. Okay. So, any questions on the material covered in this session? Okay. Yes, please. Please go ahead. Okay. So, if not, let me stop this session and then we will continue in the next session. Thank you.